This lecture is going to be on water vapor in the atmosphere. Here we can look at a map of the Earth and see the density of water vapor, the darker blue, is going to be found in and around the equatorial areas. Essentially where we find heat energy, we will be able to find water vapor. And evaporation continuously moves water from the surface to the atmosphere, and here's just kind of a quick picture that we'll make sense of here. So atmospheric water vapor. The equatorial region of Earth receives the greatest amount of insolation. This heat drives evaporation, so it should not be alarming to see the greatest amount of water vapor location that's at the greatest density in and around the equator. Find heat energy, find evaporation, find the water vapor. They're definitely linked and directly connected. So we cannot see water vapor, but we can feel it as humidity. The liquid form of water is so familiar to us that we just call it water. Water vapor has more molecular kinetic energy than ice and liquid water. And the solid form of water, which we just call ice, has less molecular kinetic energy than water vapor and liquid water. Ice molecules are closely bound to nearby H2O molecules in a temporarily fixed state, right? 2 hydrogen per oxygen. So no matter what phase it's in, a water molecule is still the same. An atom of oxygen with 2 atoms of hydrogen attached. Their energy, as exhibited by their speed of movement, is the only thing that makes them act differently in water's different phases, right? Their behavior is based on their kinetic energy, their kinetics, their speed of molecular movement. So conservation of energy is one of the very basic laws of nature. It says that energy cannot be created or destroyed, but it can change form. Heat energy can be transported from solid to liquid to gas as a part of the Earth's water cycle, or the hydrologic cycle. So when water molecules slow down enough to change from a vapor to a liquid, or even ice, the kinetic energy of their movement changes into another form of energy, heat. When water evaporates from a pond or a body of water to become water vapor, heat energy becomes the kinetic energy of the added motion of the water vapor itself. So here's a quick thought experiment. So imagine being outdoors on a hot day, call it 90 degrees. To make this thought experiment work even better, we're going to imagine that the humidity is very low. As you exercise, you begin to sweat, but the sweat quickly disappears. What is happening? Well, hopefully you realize that the sweat, which is water evaporating into vapor, into the air, that your body's heat is supplying the energy needed to speed up the molecular motion in the sweat to turn it into water vapor. So this heat is what we're going to call latent heat, and is evaporated water that is carrying away from your body, effectively cooling you off. So before we get into latent heat, we'll end with that. I want to make sure we get into relative humidity. So here goes. So relative humidity is expressed as a percentage, is essentially the water vapor content, which I'll be referring to as WVC, divided by the capacity, or the amount that a particular parcel of air can hold. So water vapor content, how much water vapor is in the air? So we can do this. We can calculate this. It's essentially the amount, how much is in there. And the capacity here is the maximum amount of water vapor that the air can hold. The air's capacity to hold water vapor varies as temperature changes. The higher the temperature, the greater capacity. And we can see it down here. 40 degrees Celsius, which is 104 degrees Fahrenheit, can hold 47 grams per kilogram of water vapor. So cooler air, 0 degrees Celsius, can only hold 3.5 grams. So we've got this capacity on this side, and we've got this understanding of temperature. Colder air can hold less, warmer air, hotter air can hold more. So relative humidity expresses how close the air is to reaching saturation at some temperature. In other words, relative humidity is a ratio of the air's actual water content compared with the air's capacity at a certain temperature. So we'll keep working on it. We'll make sense of that. So here's a graph. I think that you will best be served by putting this into graphical form. It'll allow you to get better numbers when you have to interpolate using this graph for solving problems. So the graph is a visual display. This graph is a visual display of these numbers. But used together, you'll be able to better solve problems because you'll be interpolating, and I think this will work a lot better for you. Okay, so having said that, so let's get this concept driven home. So warmer air can hold more water vapor. A parcel of colder air has less space due to slower kinetic energy motions, so it can hold less water vapor than hot air. So let's look here. I've got 3 parcels I'm going to make sure we make sense of. I've got 10 degrees Celsius, 20 degrees Celsius, and 30 degrees Celsius. So let's start with what we know, and I also have table 8-2 over here I can make sense of. So I see that at 10 degrees Celsius, this water vapor, this parcel of air is completely saturated. It's full. So at 10 degrees C, the air is at its capacity. And we'd say that this is saturated. It has a 100% relative humidity. So when I compare at 10 degrees Celsius, over here, 10 degrees Celsius, 10 degrees, I see that the capacity is 7 grams per kilogram. So when we see that there must be 7 grams per kilogram of water vapor. So this parcel of air at 10 degrees Celsius is saturated or at its capacity. Right? I see it's saturated, 10 degrees C. Its capacity is 7 grams per kilogram. I see that that's its value. But notice, at 20 degrees Celsius, we see that the air, still containing 7 grams per kilogram, simply warming up the air, of 7 grams of water vapor, it now has a relative humidity of 50%. Since its capacity is 14 grams per kilogram. Notice, I find 20 degrees Celsius on table A-2, and I find that, well, it can hold 14 grams per kilogram. Notice, it's warmer, so it's got more space in which it can contain water vapor. But in this case, it has 7 grams, it can hold 14 grams. It tells me that its relative humidity is 50%. And then at 30 grams, I continue heating it. At 30 grams, we see the air still containing 7 grams per kilogram, right? 7 grams hasn't changed. Now has a relative humidity of 26%. Since its capacity is 26.5 grams, so 30 degrees C can hold 26.5 grams per kilogram. 7 divided by 26.5 tells me 26%. So I can look at it as this ratio of how much water vapor it has compared to how much it can hold. Moving on. So relative humidity. So how are we going to do relative humidity? Well, in our classroom, we're going to be using what's called a dry and wet thermometer. As the wet bulb is the one we'll be moving. This is one we'll put a wet paper towel on. And we move it through the air and it evaporates and cooling occurs. In the drier air, or in drier air, the rate of evaporation will be higher and thus a greater cooling effect will result than in wetter or more humid air. After spinning the thermometer for a few minutes, the temperature of the wet bulb thermometer stops lowering. Record the temperature from both the dry and the wet bulb. Remember, the dry bulb is the actual temperature of the room. So the relative humidity and dew point, which we'll be adding here today, can then be determined using tables 8-3 and 8-4, simply by using your y and your x axes of data that you collected. So we're going to do an example here. So how do we find the relative humidity in the classroom? So I took a dry bulb temperature, we'll call that 21 degrees Celsius, and a wet bulb temperature. So this is the wet piece of paper towel, we'll call it 12 degrees C. So we do these in class, we run the data. If you find that I've got 21 degrees Celsius and a difference of 9 degrees C, I can do this. I can align this. I find my 9, I align it here, and I associate that with 21 degrees C. You'll find that it's located in between 30 and 33%. And I could say very confidently that the relative humidity in the classroom is in the low 30% based on these numbers here.